Welcome to the 8th lecture of module 1 of mass transfer operation. In this module, we are discussing diffusion mass transfer. Before going to this lecture, let us have recap on our previous lecture. On our previous lecture, we have discussed mainly gas phase diffusion coefficient prediction, liquid phase diffusion coefficient measurement and its prediction. So, for gas phase diffusion coefficient prediction, we have used Fuller equations and also Chapman equations. Then for the liquid phase diffusion coefficient measurements, we have considered two methods. One is the diaphragm cell method and the second one we have considered the semi empirical equation, which is Wilkie-Chang equation. Then we have finally used Stokes-Einstein equation for the determination of the diffusion coefficient in the liquid phase. In this lecture, we will consider multi-component diffusion and the diffusivity of the solid. So, first we will consider multi-component diffusion and then we will consider diffusivity in solids. Multi-component diffusion, in this case the equation for multi-component mixture can be derived using Stephan-Maxwell method. First the equation for binary diffusion will be obtained and then to be extended to the multi-component diffusion. Now, while deriving the equation for the binary diffusion coefficient and then to the multi-component systems, the following assumptions would be taken. The first one is the partial pressure difference, that is delta Pa is proportional to the Ca and Cb. Ca and Cb are the molar concentration of A and B. So, delta Pa partial pressure difference is proportional to the concentration Ca into Cb. Second one is the partial pressure difference is proportional to the length of the diffusion path, which is delta x. And the third one is the partial pressure difference is proportional to the difference in the diffusion velocities of A and B, which is Va minus Vb. So, from this assumption we can write at constant temperature and pressure minus delta Pa is proportional to Ca into Cb into delta x into Va minus Vb. Now, if we equate these two with a proportionality constant k, we can write minus delta Pa would be equal to k into Ca into Cb into delta x into Va minus Vb. Here this k is the proportionality constant. Now, if we take limit delta x tends to 0, we can write minus dPa dx would be equal to k into Ca Cb into Va minus Vb. Now, if we just multiply k Ca Cb with Va and with Vb, we can write k Ca Cb into Va minus k into Ca into Cb into Vb. Now, as we know, Ca into Va is Na. So, we can substitute Ca and Va, these two terms, with Na. So, we can write k Cb Na, and similarly Cb into Vb is Nb. So, in this case if we substitute Cb Vb with Nb, we will have minus KCA NB. So, this is equation 1. Now, we know the total concentration C would be equal to Ca plus Cb for two component system, and if we consider ideal gas, we can write Ca would be equal to Pa by RT, that is partial pressure of component A divided by R is the universal gas constant into the temperature T. Therefore, the equation A becomes this equation, we can write minus RT dCA dx would be equal to K into C minus Ca into Na. So, we have substituted over here this Cb, from here we can write C minus Ca. So, which is substituted over in this equation A. So, we will have K into C minus Ca into Na minus K Ca Nb. Now, if we multiply, we can write K C Na minus K Ca into Na plus Nb. So, from this, now if we rearrange, we can write flux Na, this one would be equal to Na plus Nb into Ca by C minus RT by Kc into dCA dx. Now, if we consider dAb would be equal to RT by Kc, then this equation we can write. So, this part is dAb. So, then we can write Na would be equal to Na plus Nb Ca by C minus dAb dCA dx, which would be equal to Na plus Nb Ca by C is concentration of A divided by the total concentration. So, it is the mole fraction of component A. So, we can write Na plus Nb into Ya minus C into dAb dYA dx. So, this is identical equation as obtained from fixed first law. Now, if we consider a multi-component mixture containing n components, if there are n components, then there would be n minus 1 binary mixture, and contribution from all such binary mixture must be taken into account. So, you can write minus RT dCi dx would be equal to summation over j is equal to 1, j not equal to I to n k I j into C j into n I minus C I into n j. This is for multi-component system. Now, if we divide this equation both sides by C and RT, it gives minus dYi by dx would be equal to summation over j is equal to 1, j not equal to I to n k I j by RT into Yj into Ni minus Yi into Nj, and we can write this as summation over j is equal to 1, j not equal to I to n 1 by C dij into Yj Ni minus Yi Nj. So, the Kij by RT we can write 1 by C dij. So, this is equation C. Now, equation B which we have derived before, this one Na would be Na plus Nb into Ya minus C into dAb into dYA dx can be extended to multi-component mixture as Ni would be equal to Yi summation over j is equal to 1 to n into Nj minus C di mix. So, this is the diffusivity of the mixture into dyi by dx. If there are two components, we have two flux Na plus Nb. Similarly, so Nj represents the flux of different components. Now, comparing equation C and D, these two equations if we compare, so we can write dim would be equal to Ni minus Yi summation over j is equal to 1 to n divided by summation over j is equal to 1, j not equal to I to n 1 by dij into yj ni minus yi nj. Now, if we considered a special case, if all the components except I are non-diffusing or inert. So, only I is diffusing species, all other components are non-diffusing or inert, that is Nj would be equal to 0 and j not equal to I, then dim would be equal to 1 minus yi divided by summation over j is equal to 1, j not equal to I to n yj by dij. So, integrating equation D, we have this is equation D, Ni is equal to yi summation over j is equal to 1 to n Nj minus C dim dyi by dx. So, integrating this equation, we have Ni integral 0 to L dx would be equal to minus C dim integral yi0 to yil dyi divided by 1 minus yi. So, if we integrate, we will get Ni would be equal to C dim by L ln 1 minus yil divided by 1 minus yi0. So, this is the equation of the flux for multi-component systems having the diffusivity of the mixture taken into consideration to calculate the flux. Now, let us consider one example. Carbon dioxide is diffusing through a mixture of nitrogen and hydrogen at 300 Kelvin temperature and 100 kilopascal total pressure. Now, at one location, the partial pressure of carbon dioxide, nitrogen and hydrogen are 40 kilopascal, 50 kilopascal and 10 kilopascal respectively, and at another location these are 10 kilopascal, 75 kilopascal and 15 kilopascal respectively. The distance between the two locations is 3 millimeter. The diffusivity values are given. dCO2 N2 is 1.5 into 10 to the power minus 5 meter square per second. dCO2 hydrogen is 7 into 10 to the power minus 5 meter square per second, and d nitrogen hydrogen is 8 into 10 to the power minus 5 meter square per second. Now, calculate the flux of carbon dioxide. Since this is an example of multi-component systems, so we have to use equation to calculate the mixture diffusivity, and then we can calculate the flux. So, the flux equation which we have derived is for carbon dioxide over here is NCO2 would be equal to C into dCO2 mixture divided by L into ln 1 minus Y CO2 at L divided by 1 minus Y CO2 at 0. Now, if we consider ideal gas, then C would be equal to Pt by RT. The system is at atmospheric pressure 100 kilopascal. So, Pt is 100 into 10 to the power 2 Pascal divided by R is 8314 meter cube Pascal per kilomole Kelvin into T is 300 Kelvin, which is given. So, we can calculate concentration C would be equal to 0.0401 kilomole per meter cube. Now, we know the mixture diffusivity equation, which is equal to 1 minus yi divided by summation over j is equal to 1, j not equal to I, yi divided by dij. So, we can calculate dCO2 mixture would be equal to 1 minus YCO2 divided by Yj would be the other two components, that is Yn2 divided by dCO2N2 plus YH2 divided by dCO2H2, which is equal to 1 minus 0.4 divided by 0.5 by 1.5 into 10 to the power minus 5 plus 0.1 divided by 7 into 10 to the power minus 5. So, here in one location it is given as 40% or 40 kilopascal carbon dioxide. So, its mole fraction is 0.4, and for nitrogen it is 0.5 mole fraction, and for hydrogen it is 0.1 mole fractions, and then the diffusivity of CO2 nitrogen is 1.5 into 10 to the power minus 5 meter square per second, and diffusivity of CO2 hydrogen is 7 into 10 to the power minus 5 meter square per second. So, if we substitute these values, we will get d CO2 mixture would be equal to 1.73 into 10 to the power minus 5 meter square per second. Now, length which is between the two location is 3 millimeter, which is 0.003 meter, and YCO2 at 0 is 0.4. The mole fraction of CO2 at location 1 is 0.4, and at location 2 is 0.1, which is 10 kilopascal at other location for carbon dioxide. So, with this, if we substitute in this equation, we can get C which we have calculated, which is 0.0401 kilomole per meter cube into dCO2 mixture, which we have calculated 1.73 into 10 to the power minus 5 meter square per second. So, which is substituted here, divided by the length, which is 0.003 meter, into ln 1 minus YCO2L, which is 0.1, divided by 1 minus YCO2 at 0, which is 0.4, which is substituted here. So, we can calculate the flux is 9.37 into 10 to the power minus 5 kilomole per meter square second. So, this is how we can calculate the flux for a multi-component system. Now, we will discuss diffusivity in solids and its application. Diffusion occurs in solid phase which comes in contact with gases or liquids in many processes such as you can see drying, adsorption and membrane separations. The diffusion in solids can be broadly classified into two major categories. The first one is diffusion follow Fick's law, that is does not depend on the actual structure of the solid, and the second one is diffusion in porous solids which depend on the actual structure and void channels in the solids. Now, diffusion in solids follow Fick's law, the first one. Like if you see that in this case the diffusion occurs when the solutes dissolved in the solid to form a more or less homogeneous solutions. For example, diffusion of gaseous component through rubber or polymer. So, it diffuses into the polymer and makes a almost homogeneous solution. The diffusion of solutes through polymeric solids is more like diffusion in liquids, particularly for permanent gases. Gas dissolves into the solid exposed to the gas and usually described by Henry's law. So, in this case the gas which will diffuse to the solid materials forms the homogeneous solutions, and the solubility of the gases into the solid obeys Henry's law. The gas diffuses from high to low pressure side. The polymeric chains are in a state of constant thermal motion and diffusing molecule move from one location to the adjacent location due to the potential barrier. An Arrhenius type equation may be applied for the temperature dependency of the diffusion coefficient in polymers. So, this is the relation of diffusion coefficient, which is Arrhenius type of relation, where we can write dA would be equal to d naught e to the power minus Hd by RT. Here Hd is the energy of activation, d naught is a constant, and R and T, R is the universal gas constant and T is any temperature. For the permanent gases, the typical diffusivity value is in the order of 10 to the power minus 10 meter square per second. So, this is the typical value, but it varies from 10 to the power minus 5 meter square per second to 10 to the power minus 13 meter square per second. Now, if the diffusivity is independent of concentration and there is no bulk flow, the steady state molar flux Na in the x direction is given by Fick's law as follows. Na would be equal to minus dAb dCA dx. Here dAb is the diffusivity of A through the solid. Now, integration of this equation gives diffusion through a flat slab of thickness L. So, if we integrate this with a thickness of the slab of solid materials L, we can write Na would be equal to dAb Ca1 minus Ca2 divided by L. Here Ca1 and Ca2 are the concentration at two opposite sides of the slab. For other solid shapes, general equation for rate of diffusion is, which is defined by W, would be equal to Na into S A average. S average would be equal to dAb into S average into Ca1 minus Ca2 by L. So, S average is the average cross sectional area for diffusion. So, basically this W has a unit of mole or kilomole per second and Na is the flux which is kilomole per meter square second. So, if you take Na whose unit is kmol per meter square second and S average, the cross sectional area is in the unit of meter square. So, if we multiply Na into S average, it would be kilomole per second. So, this is the rate of diffusion or diffusion rate in terms of kilomole per second. Now, diffusion in solid follow Fick's law. The diffusion coefficient in the solid is not dependent on pressure of the gas or liquid on the outside of the solid. For example, if carbon dioxide gas is outside a slab of rubber and is diffusing through it, would be independent of pressure of carbon dioxide at the surface. The solubility of carbon dioxide in the solid, however, is directly proportional to the partial pressure of carbon dioxide. So, the solubility term of a solute gas A in a solid is usually expressed as S in meter cube solute at STP of 0 degree centigrade and 1 atmosphere pressure per meter cube of solid per atmosphere partial pressure of A. So, S has the unit of centimeter cube STP per atmosphere centimeter cube of solid in CGS system. To convert this to Ca, that is concentration in solid in kilomole per meter cube using SI unit, we can write Ca would be equal to S meter cube STP divided by the meter cube solid into atmosphere divided by 22.414 meter cube STP divided by kilomole of A into Pa atmosphere, the partial pressure of component A. So, it would be S into Pa by 22.414 kilomole of A divided by the meter cube of solid. Now, let us consider another example. Carbon dioxide is diffusing through a polyvinyl alcohol membrane of 200 micron thickness at 70 degree centigrade and at 10 kilopascal partial pressure. The pressure of carbon dioxide on the sweep side of the membrane is assumed as 0. The solubility of carbon dioxide in the polyvinyl alcohol membrane is 0.007 meter cube STP of 0 degree centigrade and 1 atmosphere pressure, and the diffusivity of DAB, the diffusivity of component A, that is carbon dioxide into the solid, is 5 into 10 to the power minus 10 meter square per second at 80 degree centigrade. Calculate the steady state flux of carbon dioxide. So, we can write C carbon dioxide, that is concentration of carbon dioxide at site 1 is equal to S meter cube STP by meter cube solid into atmosphere divided by 22.414 meter cube STP per kilomole A into PCO2 atmosphere. So, if we substitute over here, we can write S is 0.007 meter cube. So, 0.007 and then the partial pressure is 10 kilopascal, which is 0.1 divided by 22.414 kilomole carbon dioxide per meter cube solid. So, this would be equal to 3.123 into 10 to the power minus 5 kilomole carbon dioxide per meter cube solid. So, we have calculated the concentration of carbon dioxide. Now, at 2, that is on the other side, the concentration of carbon dioxide is 0 because it is considered sweep side pressure is 0 and the thickness L is 200 micron. So, we can write 200 into 10 to the power minus 6 meter, which is 2 into 10 to the power minus 4 meter. Now, if we substitute these values in the flux equation, we will have diffusivity of carbon dioxide into the solid, which is 5 into 10 to the power minus 10 into 3.123 into 10 to the power minus 5 minus 0 divided by 2 into 10 to the power minus 4, which is equal to 7.81 into 10 to the power minus 11 kilomole carbon dioxide per meter square second. Now, diffusion in porous solid. So, if we have the solid materials which is porous in nature, the structure of solid and interactions with the solutes are important for the rate of diffusion. The solid sometimes may act as porous barrier or as porous catalyst palette and is normally surrounded by a single body of fluid. The inward or outward movement of the solutes through the pores of the solid is mainly by diffusion. This movement may occur inside the pore or at the surface of the adsorbed solute. Now, diffusion inside the pore. When the diffusion occurs inside the fine pores of the solid at low pressure, the mean free path of the molecules may be larger than the diameter of the passage. The collision with wall becomes important in this case compared to the collision among the molecules. This kind of diffusion is known as the Knudsen diffusion, and you can see the solute molecules passes through the channels and collide with the wall of the passage, and in this case the mean free path of the molecules is larger than the diameter of the channel. So, this we can call the Knudsen diffusion, and in this case the collision with the wall is important compared to the collision among the molecules. So, this is observed when the pore size is below 50 nanometer, as in the case of intraparticle diffusion in a porous catalyst. So, when the diameter of the pore is smaller than 50 nanometer, Knudsen diffusion becomes predominant. Now, to quantify Knudsen diffusivity, a simple equation based on kinetic theory of gases was proposed as follows. That is, dk would be equal to 2 by 3 into Rp into V, where Rp is the radius of the passage and V is the average velocity of the molecules due to their thermal energy. Now, this average velocity due to their thermal energy can be calculated as follows. V is equal to 8 RT by pi m to the power half, where T is the temperature in Kelvin, m is the molecular weight and R is the universal gas constant. The flux due to Knudsen diffusion is similar to the Fick's law, and we can write Jk would be equal to minus dk dCA by dx would be equal to minus dk by RT into dPA by dx. Now, let us take an example. Carbon dioxide is diffusing through a pore of catalyst at 400 Kelvin. The diameter of the pore is 50 angstrom. Now, we need to calculate the Knudsen diffusivity of carbon dioxide. So, Rp over here, the diameter of the pore is 50 angstrom. So, which is 50 into 10 to the power minus 8 centimeter. R is the universal gas constant, we know 82.1 centimeter cube atmosphere per gram mole Kelvin. Now, 1 atmosphere we can write in CGS unit 1.013 into 10 to the power 6 gram centimeter per second square per centimeter square. T is the temperature, which is 400 Kelvin. Now, M is equal to 44 gram per gram mole. If we use the equation for diffusivity, dK would be equal to 2 by 3 into Rp into V. So, now if we substitute the equation for V, which is 8 RT by pi m to the power half, then it would be 2 by 3 into Rp 8 RT divided by pi m to the power half. Now, if we substitute, it would be 2 by 3 into Rp is 50 into 10 to the power minus 8 into 8 into 82.1 into 1.013 into 10 to the power 6 into 400 divided by pi into 44 to the power half. So, if we solve it, it would be 0.0146 centimeter square per second. So, this is the values of diffusivity, Knudsen diffusivity through the pores. Now, another thing is the surface diffusion. The diffusion of adsorbed molecules on the surface due to concentration gradient is known as the surface diffusion. If the fractional coverage of the surface is less than unity, then some of the active sites remain empty. So, in that case, what happens? Adsorbed molecules having energy greater than the energy barrier tends to migrate to an adjacent vacant site. So, this migration is visualized to occur by hopping mechanism. So, this type of diffusion is known as surface diffusion, where the molecules diffused from one active site to the other active sites or adjacent active sites which are vacant through the hopping mechanism. The flux due to surface diffusion may be written similar to Fick's law, which is Js would be equal to minus ds into dCs by dx. Here ds is the surface diffusion coefficient and its unit is meter square per second. Cs is the surface concentration of the adsorbed molecules, which is kilomole per meter square. So, please note that the surface concentration unit compared to the bulk concentration unit, the bulk concentration we generally define by the unit of kilomole per meter cube, but surface concentration is defined by kilomole per meter square, that is the unit surface area. So, Js, the number of moles transported across unit distance on the surface normal to the direction of transport, is in the unit of kilomole per meter second. So, thank you for attending this lecture, and we will discuss in the next module, that is module 2 is the interface mass transfer.